Hi everyone, today we are building a CNN model that classifies 30 categories of musical instruments, and we will use TensorFlow and Keras. We will load and normalize the images from the training dataset and then build step by step a convolutional neural network that contains all the relevant layers, and we will add a dropout, early stopping, and checkpoints to get the best accuracy. After that, we will test our saved model. We will do it in two steps. First of all, we will try it on random images, and we will generate predictions and compare it to the true labels. And after that, we will build a full confusion matrix that help us to understand how well perform our model. So let's start. So let's run a short demo and explain what we are going to do today. We will take this dataset, which conclude 30 musical instruments. For example, if you open this one, this is an accordion images. You can see lots of shapes and lots of colors. Another instrument maybe here, this one, the sitar. So you can see there are many images, and basically we would like to run a convolution model that can classify those images, those musical instrument images. So we will do it on two parts. First of all, we will build our model. We will learn how to create the structure of the model and run the training and explain the parameters and how can we twist the parameters to improve the model. And then we will test our model using some test images. First of all, we will test one image by picking a random image from the test folder, and then we will run a confusion matrix for all the images in the same test folder. So let's run the code and it will be more clear. We will load our saved model and then pick a random image, and you can see that it picked a piano image, and the true value, of course, this is a piano, and the model predicted it as a piano. So this would be the first step of running inference of our model. And the second step will be running through all the test images, and then we will display a confusion matrix, and we can see how the model predict those test images. So you can see that the most of the samples are on this line. For example, this one is a Castagnetes. The Castagnetes have 5 samples, 5 images, and the true values are the same as the predicted values. So it will predict Castagnetes. This is the main concept. We will learn how to create this model and how to run an inference through a random image and through all the test image. And most important, this tutorial is part of this playlist. You are most welcome to subscribe to my channel and also subscribe to my mail list, and you can find more classification tutorials in this playlist. So let's start with the installation. First of all, it's better that we will run it on the Linux environment, since we are going to use TensorFlow, and TensorFlow has the ability to use the GPU card in a Linux environment. So you have to run if you are using Windows, you have to run and install a WSL under Windows. If you are running on a Linux machine, so it's not important which distribution you are using, just use a Linux environment. So let's start with the installation. I will switch between this command prompt, which is a PowerShell, and this install install.txt file that contains all the instructions. So let's start with creating a new Conda environment. It will be based on Python 3.11. So let's copy the command, or you can of course type it. Conda create TASM. I decided to choose this name. It's just a custom name, but of course you can choose your own custom name for this environment. So let's wait a few more seconds and the environment will be ready. So now it's ready. Let's activate the environment. Conda activate, and it is TASM. Great. Let's do clear the screen. You can see here on the left side that this is our current environment. Let's go back to our install file. So now we have to install TensorFlow, and you have here a full instructions for installing TensorFlow. 1 second, that's it, that's better. And it's really important, first of all, to understand what is your CUDA version. So you can run this command, nvcc version, and if I run it, 1 second, nvcc version, you can find what is your CUDA version. You can see mine is 12.6, and if you go to this link, you can see all the relevant commands for each CUDA version. For 12.x CUDA, it's a very simple command: pip install TensorFlow and CUDA equals 2.17.1. If you don't have a GPU card, you can run it of course on a CPU environment, and the command will be without the end CUDA. Just copy and paste this command. So I have a GPU card, so I will Ctrl V, and now I'm installing TensorFlow 2.17.1. I recommend that you will install the same version so we can get the same results and you can keep up this tutorial. So I will stop the recording and we'll continue after the TensorFlow will finish the installation. So we finish the TensorFlow installation. Let's go back to our file. So now we have to install these 4 packages. So once again, I will run it and then we'll continue after the installation. Great. And last phase, we have to run the VS Code. So in order to run the VS Code, you should type code space and a dot, and this will run the VS Code. So here it is. So this is our VS Code. So I've already launched the VS Code. So let's go back to the one that I'm using already. So this is our VS Code. It's very important to run the VS Code from the Linux environment. And now in the VS Code we have to change the current working Conda environment. So we have to type Ctrl, Shift and P, all the 3 keys together, and then this menu will pop up and we have to choose select interpreter. So now let's choose the one, TASM. Let's choose it. So this is now our current environment. The last step is downloading the dataset. The dataset contains images of 30 musical instruments. This is the link for the dataset. Let's jump to our browser. You can see this is the 30 musical instrument dataset. This dataset has more than 5,000 of images, and it's divided to validation, train, and test. So basically download the dataset, and now we are ready to start coding. So let's start coding. First of all, we will create a new and fresh Python file. In this Python file, we will create our model and do all the training stuff. So let's name it build CNN for 30 musical instruments. First, let's import the core libraries we'll need. NumPy for number crunching, pandas for handling data tables, and matplotlib for plotting the result. Now from Keras, I'm bringing in some utilities to load and process images. Also, we will use callbacks like early stopping and model checkpoint that will help us to manage the training. And of course, Adam Optimizer from TensorFlow to update our weights efficiency. And after that, we will import Tensor itself, and then we will build our CNN using a sequential API and adding the relevant layers that we are going to use, like dense, flattens, conv2d, max pruning, and dropout. Now let's define the path to our dataset. I've got the training folder and the validation folder with 30 categories of musical instruments. I already downloaded and put it on my local machine. I chose a custom name. Of course, you can choose your own folder name for storing those images. Now let's also define and set parameters like the bed size, the image size for training, and the number of epochs. Next, before diving into the training, and let's actually visualize one sample image, and this just helps us to make sure that our data is loading properly. So we will use the load image function. Let's choose one of the images from the accordion subfolder, image number 10. And let's display it using the pyplot, and let's also print the shape of the image. Just fixing the direction of the slashes. Also it's accordion with one C. So let's run it. Great, so this is the image of accordion. Now we are ready to continue. Now let's load the training dataset directly from our directory, and we will use the TensorFlow utility image dataset from directory, and this will make it super easy. I'm setting the label mode to int because we will use a sparse categorical cross entropy later. So we will load the images, convert them to our custom image size, and collect them on our bed size. After that, images come in as pixel value between 0 and 255. So to help the model train better, we normalize them into between 0 and 1 range. So this is the normalization process. Now for performance, we cache and prefetch the data. This means that while the model is training on one batch, the next batch is already loading. Now comes the fun part, building our CNN model. I will wrap it inside the function so we can reuse it easily. Let's name this function getCNN model. And of course it will be a sequential model. First convolution layer with 32 filters and ReLU activation. Padding set to same to preserve spatial dimension. And after that, a second convolution layer with 64 filters. So let's finish the first layer. Of course, we are adding a max pooling. This is a classical CNN model. So this would be our two first layer. And now we are adding the second layer that is based on 64 filters. And of course adding another max pooling layer of a 3x3. Third convolution layer will be with 128 filters. Now we are flattening to connect to a dense layer. and first dense layer would be with 256 neuron and a ReLU activation, and another dense layer with 128 neurons, and finally the output layer would be with 30 units, since we have 30 categories, one for each class, using a softmax. Next, we will compile the model with the Adam optimizer and sparse categorical cross entropy. So we are closing this function. Let's create the model and print its architecture summary. Let's run it. So the target is to see that the model was created successfully, and we can get a summary of the model. Please notice the last layer is our 30 category, so it seems okay. Next, let's set up a callback. At first, a model checkpoint will save the best model during training. So let's define the path for storing our best saved model. That means that each time when we are finished an epoch and we are getting a better result, we will store our weights in this location. And the model checkpoints that we will don't lose progress if the model starts overfitting. This is the main target. We are going to follow the validation loss. That means that each time the validation loss will be lower, that means our model progress is better, and we will save the model. Early stopping will halt training if validation loss doesn't improve for 30 epochs. This saves time and prevents overfitting. Now it's time to train the model. We pass in our training and validation dataset, set the number of epochs, and add the callbacks for best checkpoints and early stopping. After we finish the training, let's save the final model to the disk, and even if early stopping triggered, we still have this as a backup. Now let's visualize how training went. We will plot accuracy and loss for both training and validation set. Okay, let's run the code, but before run the code, let's reduce the batch number. I believe it's a high value for the first time. Let's try run it with let's try it with 16 and run Python, and let's see the result. So we're starting the first epoch out of 200, and I believe that we have an out of memory. So basically we have two solutions. One, try to reduce more the batch size, for example to the value of 8, and another direction will be reducing the size of the image. So we will try to load it to a lower value. So let's try both approaches. First of all, let's try to reduce it to the value 8, and if not, we will try to add to reduce also the image size. So first of all, we're reducing the batch size. Let's run it and see the result. So it starts training, and still we have an out of memory error. Let's stop it, and let's reduce it to 128, and do the same here. And let's run it again. So now it seems better. We don't get the error message about the memory usage. So I believe that now we will follow the training. First of all, you can see that each time that we are getting a better results, mean better accuracy and better validation loss, we are saving the model here. So here the validation loss was improved from 1.81 to 1.64. So this is a result for an improvement. If there will be no improvement during 20 improvements, it will stop the training. So let's, I believe that we will stop here the recording and we will continue after the training will be finished. So the training has finished. So you can see here the training accuracy and the validation accuracy. And also on the right side we can see the training loss, the blue line, and the validation loss. Moreover, if we go here, we can see that it stopped after 31 epochs. So although we asked the model to run for 200 epochs, there was no improvement for 20 consecutive epochs. So the model stopped the training after 31 epochs. I would like to do another training. So let's enlarge the parameter, the one with the 20 early stopping. Let's find it, and I would like to change it to a higher value. It is. Let's change it to 40. And let's run it again. And after that, let's see if there is a better result. And we will continue after the training will be finished. So the second training was finished, and now it's ran about 55 epochs. It's not really the best result if I'm comparing the training accuracy and the validation accuracy. I think we should add more layers and train it more, but as for this tutorial, it will be good enough. And let's continue for running inference of our model and test it on our test folder. Now let's create our second Python file, and the main target is to test our model. We would like to code an inference process using the test images folder. So let's start by importing the session libraries. We will need OS and random for file handling, and matplotlib will help us to visualize the result. At first, let's set the path to our test dataset and the trained model we saved earlier. We can copy it from the previous Python code. It will be simple. Just copy the full path and replace it from train to test. Also, let's copy the path for our weights file, the best model saving during the training. We also define the target image size and list all the class names from the test folder. And after that, let's load the trained CNN model we built earlier. And if everything works, let's print a success message. Let's run it and see the result so far. Let's wait a few more seconds. So here are all the classes, the 30 classes of musical instrument, and also the model was loaded successfully. Now let's divide the testing process to two tasks. First of all, we would like to predict a random image from our test folder. So I will create a function that randomly picks an image from the test set and run it through the model, and then shows it will display the predicted label. So this is the function. I name it predict random image. First, let's pick a random class. Basically, it's a random subfolder, and then we will pick a random image from this random folder. And now we will load this image using OpenCV and convert it from BGR to RGB. Then we will resize our image to 128 by 128. Then normalize the image so it will be the values of the pixel will be between 0 and 1. Also, let's create a batch of images that contain one image, because this is the required, this is what we need for our model. And now we are doing the prediction process. We are sending our image to the model and running the inference, grabbing the class index. And next, let's get the class name. So the class index will have a number between 0 and 30, and now let's get the class name that will be the name of the musical instrument. And the final step is displaying the result. First of all, let's create a figure using pltplot. Let's display in the title the predicted class name and the true value. The true value, basically, it's the name of the subfolder when we extract and grab the image. And this will finalize the first step, which is displaying a one random image. So let's run the code. Now we will collect a random image, run a prediction, and display the result on our image. Great. As you can see here, the true class, this is a tuba, and the predicted class is the same, tuba. Let's run it again. Let's see if we are getting the same result. The true label and the predicted label are the same. So now it picked a harp, and once again the predicted value and the true value are the same, so it's a very good prediction. Let's run the third one and the last one, and here it is. And now it detected a clarinet. Once again, the true value and the predicted value are the same. Great. Let's continue to the next step. Now let's move to task number 2. And in this phase, we would like to evaluate on the entire dataset. So we will create another function that loop through all the test images, run a prediction, and then we will build a confusion matrix and a classification report. So as you can see, we are running through all the test images. We will loop through every class folder and each image inside it. Then we load and pre-process the image just like before. And after that, we will run the model prediction, doing the same process, grabbing the class index and the class name. And after that, we save the true and the predicted label for later evaluation. Now, once predictions are done, we will generate the confusion matrix. and we are sending the true labels and the predicted labels, and next we will visualize the confusion matrix using Seaborn, and we will also print out a full classification report. So basically we are generating a full confusion matrix, and we can compare all the true labels and all the predicted labels, and we can see the performance of our training. We have to indent this code, and now I believe it's ready, so we can run it. So let's run it and see the result. In the first part it will be the random image, so let's skip it. So this is our random image. In our case now it's a sitar. And let's continue to the confusion matrix. So you can see in the log that it loads all the test images, and in a few seconds it will generate the confusion matrix. And now, as you can see, and there are 30 true labels here on the left side and 30 predicted labels here on this side, and for each category we can find the relevant same category in the true and in the predicted. And if it is a good model, we're expecting that all or most of the result will be here on this line. For example, if we take the drums and if we follow this line, we can see that there are 5 test images of drums, and all the true labels are equals to the predicted labels. Here are the true labels, there are 5 of them, and they are equals to the predicted labels. And here, for example, in the flute, only 3 of them are the same. There is one true label of flute that was predicted as maracas, and there is another true label of flute that was predicted as didgeridoo. I don't know what is this musical instrument, but you can understand that most of the value, and this is the most important, most of the values are here on this line. That means that we have a very good model. So thank you very much. I hope you enjoy this tutorial. You are most welcome to subscribe my channel. More tutorials will be uploaded soon. Bye bye.